Welcome to everyone, and thank you for being here to this afternoon session. This afternoon session is organized around two lectures, that of Professor Xiao-Li Meng, who is at the moment connected with us via web. And the second lecture is presented by the Professor Annette Baudisch, who is present in person here. Okay. Well, let me briefly present the first speaker. Professor Xiao-Li Meng is professor of statistics at Harvard University. He's an eclectic scientist, an expert in many fields of statistical theory and foundation issues in statistics, but also in computational statistics and application in natural, social, and medical sciences and engineering. He has, having thus received numerous awards and honors for his more than 150 publications. So I would like to say to Professor Meng to present his lecture. Please, sorry, you have 45 minutes to present your presentation.
Thank you very much. First, I want to check if everyone can hear me well. Yes. Great. Thank you all, and thank you for inviting me. And I deeply regret that I cannot be there in person. I was prepared to come. I made all the arrangement, but unfortunately, I think this COVID just drives everybody nuts. That I probably have some kind of long COVID symptoms that and the doctor advised not to make these long trips. But I'm hoping that I would do a good job today. That you will invite me when you celebrate 1,000 years. That's I'm looking forward to. And I look at the program there, I feel it's absolutely wonderful. I'm so sorry that I will miss all these talks. I probably can watch online. And so what I want to present today is something that I started to work on about 10 years ago. And when I was asked to write this article, the COPS 50th anniversary volume for this past, present, and future of statistics, I was particularly asked to write something for the young generation. By the way, everybody looks younger as my age. That for the, what are the big problems that we face, interesting intellectually, foundational problem we face as we move forward. So I wrote three kinds of problems, that what I call the multi-source, multi-phase, and the multi-resolution. And the multi-source refer to the increasing need. We need to integrate data from all kinds of different sources, and I don't mean just different size, but different quality, different type. As many of you know, that has been increasingly important problem that we need to work on. The multi-phase one referred to another phenomenon, which these days it's extremely rare that we analyze the data we collect. Most data we analyze, or other people analyze, that they are being collected by someone, pre-processed by another, maybe another processing, and there's a whole, many parties get involved. Even everybody does their best job. They're making different assumptions. They have access to different resources. They have different goals, that you end up with having this phenomenon called the incongeniality problem that I proposed many years ago in the multiple imputation content. Essentially, you have this incredibly interesting phenomenon that everybody does the best, but when you combine all this thing together sequentially, you end up with an inference is not even valid. So that's another different talk. And but the third part is what we'll be talking about today, is this idea of multiple resolution. And I was really inspired, or rather I say, well, I was pushed by this whole discussion about now we can have a personalized, inference, personalized treatment, and many different ways. Treatment does not necessarily mean medical treatment. You have education program, you have personalized marketing. You're probably the worst part is you have a personalized news. You always get the news you want to here. And so I started thinking about what exactly do we mean by personalized, and how do we ever, as a statistician or as a field of statistics, to collect the data to provide evidence, say something's personalized. And so that's essentially how I got started thinking about it. I have to confess that this is the first time I do a research, I guess, that I really did not know where I was going. Most time I had a rough idea where I was going. I thought this will be mostly put down some terminology, more a conceptual type of work, maybe helpful, maybe not. But what I did not realize, and this is part of thing I'm reporting today, is that it actually has really interesting mathematical consequences. And it's essentially on the boundary between being stochastic or being deterministic. And I know there are many experts in the room that I would working on either side, and I would also love to get some feedback today. And I know there are some discussions which I'm really looking forward to hear from them. So as I said, my first article was in this 2014. Then with my wonderful student Kelly Liu, that we wrote a couple of them, which is really apply the idea to the inference side. But today, what I'm going to talk about is the work that I published last year with another wonderful student, Xiao-Li, who's currently at the University of Illinois Urbana-Champaign, who really did all the hard mathematics, as you will see here. They're not hard, but they're tedious in a way that really pushed this my kind of a conceptual framework into something really interesting mathematically, and probably has some thought-provoking phenomena here that I like to share with everyone. So I wanted to start my talk formally with a quote from Michael Jordan and his co-authors, and they've written an article for Harvard Data Science Review. I guess it's probably not very subtle. You can see on my background that I'm promoting Harvard Data Science Review. I am the founding editor-in-chief, and I'm very proud of this new forum for anything data science and data science for everyone. It's complete free, so you can check, but probably not now. So this particular article was about Berkeley has done a fantastic job in promoting undergraduate education broadly on data science. They have this course called a Data Science 8. And this was the article, a discussion article I invite everyone to read, even if you don't care about education, because there's lots of thinking there. Particularly Mike has been promoting this idea of computational thinking versus inferential thinking. And I know most recently he's talking about economic thinking. But in this particular paragraph, what he and his co-author wrote is really about what exactly is a data science. Why that is so anything different from what we particular statisticians have been working on for really a century. And you will see that what they talk about here say, let me just read it because it's important. Whereas previous generations were in possession of data about general phenomena, we are now in possession of data about specific phenomena. For example, in genomics, we have data about each individual gene. In astronomy, we have data about each region of the sky. In medicine, we have data about each tumor. And in social science, we have data about individual humans. Well, era is about data and about specific context. In that sense, data science has an appropriate and useful terminology for capturing current trends. So what this paragraph re-emphasizes is that because the amount of data we have, or at least we think we have, we're trying to ask the questions with in my terminology, and I would convince you it's a very useful one, with a higher and higher resolution, and down to individual. Now, interestingly, I particularly like this paragraph because you can see what do we mean by individual is a very, very different notion, depends on which field you're in, right? We probably think about individual genes as something invisible by naked eye. On the other hand, astronomers talk about a region of sky, which, probably the whole Milky Way itself probably is just one individual, right? So you have this enormously different scale, but they all share some commonality. Particularly here is if you only have something unique, have a one, how do you make inference at all, right? That was the whole notion of statistical inference, at least to now, mostly is about collecting samples to infer about population. It's an aggregate effort. But when you're down to individual, and how would you even conceptually, what would you think about, right? So that's essentially how it got me to really intrigued me to think this idea. Now, so let me just give you the kind of schematic thing that, talking about promise of big data, treatment for you based on data from people like you. That's great, because I like to be treated, particularly for now, I have this condition, prevent me flying. I want to be treated as soon as possible so I can fly to see you guys. But unfortunately, no one's perfect like you, right? Because every one of us is unique. If we really talk about not even just our genetic component, even talk about environment, talking about parents, talking about siblings, right? Because all relevant for your medical treatment. Then we soon will become unique. I think this notion that contemplating between thinking about population risk versus individual risk, I don't have to remind everyone, is how relevant it is for the COVID-19, right? Every one of us these days, whatever we do, back in my mind, or maybe in the front of your mind, you'll be contemplating some kind of risk. Would I get sick if I go to this party, right? Would I, run into problems here and there? But the data we have is almost in the COVID cases, unless you have been collecting your own data, the most information you have are some kind of an average aggregate information about a population. Then you try to put yourself in the most relevant population that you can find, right? But you know that you can never be perfect, okay? Never be perfect in the sense, find the perfect data for you. So this is when I started to formulate this thing, I realized that, we all have all these data. We all know in statistical literature, certainly for the past, 20, 30 years now, that we talk about large p, small n. What I realized that if you really think about individualized, you're pushing to the boundary, or extreme boundary. We're talking about p, the number of parameters or features is essentially infinite, because there's indefinite numbers you can go on if you want to. On the other hand, because each of us are unique, direct learning, meaning that have direct sample from us, in most cases is n equal to 0. Now, it happened that the Harvard Data Science Review just published a special issue called N of 1 trial. There are this notion that you can be your own placebo or control. If you have a chronic disease, you can alternate between different treatments, so you can have a little bit of a have a little bit of control compared to yourself. Even there, if you take into account the component of time, at any time, any individual of us is still unique. So if you really push, theoretically, if you push to the boundary, we're dealing with a problem with p equal to infinity, n equal to 0, mathematically speaking, at least. So you say, well, Xiao-Li, great. You just made everything possible, because we know how hard it is p over p large, p small n. Like, can anything be said, anything be done in such a phenomena, in such a situation, other just kind of a talk it, in some rhetorical fashion? Well, I was surprised by when I pushing this, particularly with the help of my student, we actually got some non-trivial results, and I want to share with you. Okay. So the notion here that essentially is when you think about something the individualized, you are basically pushing kind of a soft matching, which is, people are just like you in the sense of your age, your gender, your exercise this level, your blood pressure, so on and so forth. Two, it's really hard matching in the sense that I want someone just like me. The question is that possible? Of course, that's not possible, but what do we do about that? Well, fundamentally, if you think about this is nothing new. This is just the classic Bias-Variance trade-off, although that Kelly and I, we give it a new name, relative new name, we call the relevance versus robustness trade-off. Relevance means here that if you find people more and more like you, whatever the conclusion you draw from them will be more and more relevant for you. Unfortunately, as you match more and more, your available proxy population size goes down pretty quickly. So the answer from those people will be not robust in statistical sense, because it's just, it depends on individuals who you happen to find. On the other hand, you can always, relax your criteria to call it being individualized. If you do that, you can find many, many people. For example, for me, if I have a disease, I say I'm a male, so I can find lots of male. I can probably even match my age. There's still lots of people. The question is, whatever I find from that population, how relevant it is for me, right? So you can see that once you start thinking about that seriously, you realize that there's always a trade-off here, right? Nobody would say, well, Xiao-Li, you're being stupid. Well, when we talk about individualized, we don't mean like going down to like teeny-beeny details, right? Who would do that? I would agree. But then my response will be, okay, then how individualized is individualized? Where do we stop? How do we even quantify the notion of being individualized? That eventually got me into a philosophical literature, because the question about what is individuality is really a philosophical question. Well, it turned out that in the philosophy, if you don't look too far, that it's actually this notion we're contemplating here is really not new notion at all. That's how our human brain essentially works. So here is something by probably the most famous ancient philosopher as well as surgeon, Galen, that he talked about the transition to similar, right? There is this notion in philosophy called the transitional inference, which is an empiricism concept. The articles I recommended will be by Huggins. I think he's from University of Arizona. Is one of the few philosopher articles that are actually very easy to read. So I want to just show you what Galen was talking about. Of course, these are translated by Hawkinson. And I thought it was amusing to me, because in this paragraph you will see Galen was both thinking as a frequentist as well as a Bayesian. Of course, none of these terms even existed back then. But bear with me to read through this paragraph, because I think it's really quite important how we think about this kind of issues. What he said is, in cases in which there's no history, or in which there's none of sufficient similarity, there's not much hope. Translate to the modern language, essentially said, if there's no prior knowledge, there's not much going on, okay? I think the Bayesians would agree with that. At the same time, and the same thing is true in the case of transference of one remedy from one element to another similar to it. One has a greater or smaller basis for expectation of success in proportion to the increase or decrease in similarity of the element, whether or not history is involved. That's a very frequent statement, right? Basically saying, how do you do those things? You look at the similarity measures. You look at the frequency, well, literally the proportion. You look at how often in the past is successful something, then you transfer that become an expectation of the success in the future, right? So that's essentially what we do, in fact, is basically we now finally populations, we look at the outcomes from that average outcome, then we say, I probably looks like that population, therefore whatever the thing can be transitioned to me. That's what the transitional inference mean, as a transition to similarity. What he also talked about, the same goes for the transference from one part of the body to another part. Expectation of the success varies in direct proportion to the similarity, right? That's an incredibly strong statement, a frequent statement, as well as in some sense a Bayesian one, because you think about similarity is summarized past, past experience. So the job I set myself to do here is, how do we formalize this notion mathematically, or at least probabilistically? How do we put a language we are all familiar with, that we can do some formal investigation instead of like Galen, basically, he's a philosopher, he's thinking about those things, he practiced this in his own practice, we practice all the time. Anytime in life we make a decision, we think about something similar, right? Or past experience, right? Then we somehow have the leap of faith and jump into whatever we need to make a decision. We engage in that process constantly. We may or may not be even aware we're engaged in the process. In fact, most time we're not aware, because if we're aware, we probably won't be able to make decisions so quickly. We start casting doubt whether the similarity is really that similar. So, so what I want to now really talk about is how we think about this from a rigorous probabilistic statistical perspective. Now let's start with this whole notion of causal inference, right? Let's think about in the medical treatment. What do we really want to know? What we really want to know is that we want to know that if we give you as an individual, I use a smart face here, a treatment A and a treatment B, we like to know that how would you respond to each treatment? Then if we have that information, or if we had that information, we can choose one, say, which one's better for you, right? It's a very simple notion. Very unfortunately, of course, we know that cannot be done before we treat you, right? Logically, because, if I treat you, I'd already treated you. How would I choose a treatment to treat you before I treat you based on the treatment for you, right? So what do we really know? In current, in vast majority situations these days, we have is this clinical trial or maybe observational study that we have a bunch of people from which we know they were given treatment A. We have a bunch of people we know they were given treatment B, and none of the people gets the same treatment. Other than now you have this N of 1 trial, but it's still at a different time. It's a very interesting field. So I encourage people to look into it. But here in the classical setting is that first, no one gets 2 treatment, and the second is none of them is exactly you, right? So as I already said, the strategy here is trying to construct a population of relevant individuals with which to approximate you. And in the machine learning literature, probably people will be very familiar. You're thinking about all kinds of training, samples, and whether the training sample is relevant, or you have the problem of covariance shift. It's all relevant to the discussions today, right? So at least, conceptually, how would you creating a relevant subpopulation? Well, you first try to define relevant in what aspect, right? So you probably predetermine a set of what they call intrinsic, has to be pre-treatment characteristics to match people on. If you match people on the post-treatment characteristics, you run into all kinds of confounding factors. It can be done, but it's a lot more complicated. So let me stay with the simpler notion that you create a population, a treatment, a process population, which has something that intrinsically, for example, your age, your gender, so on and so forth. And now I'm going to formally borrow the language from wavelets. So basically, the language I use here, because years ago I had a little bit experience working the wavelets, working with engineers on camera, how do you recover these best color? And there's this notion. So I learned a little bit about wavelets, which then later when I thought about this whole thing, I said, hey, here's the perfect mathematical framework, because there you talk about multiple resolutions, right? For those of you familiar with the wavelets, there's this notion called the primary resolution. And the idea of primary resolution is that any resolution is lower than this primary resolution that we consider as signal if there's any variation there, and anything higher you would consider as noise, right? So basically, schematically, and I think I've literally borrowed this probably from one of Dave Donahoe and Ian Johnson's article. Let's say that schematically these are the wavelets coefficient. Each line, each row is a different resolution, and you will see the red color here are these high resolution ones. There's a lot more kind of idiosyncratic variations, and they're the low ones probably point out the frequency and the location from which there may be something worthwhile to take a note of, right? So let's say the way we try to match in this very schematic way is that at the resolution R, anything is black here, which is the lower resolutions, I want to match people exactly. Anything higher than that, I would say, I don't care, because these are like a noise. In fact, I don't want them to match, because if everything's matched, I will have nothing for me to use to assess variability, right? So this multi-resolution is a very clever way of saying, I have a data, I'm going to separate them, I'm going to have part of them as my signal, and the other part I use to reserve them as variations for me to assess both the uncertainty in my study, as well as probably all kinds of uncertainties that I fail to capture, right? So this is the whole notion. So so this is essentially the mathematical language I'm going to borrow, okay? So again, schematically, we're going to try to look at the high resolutions. So the mathematical language I'm going to borrow here is something that some students are afraid of, but I really hope students now should pay attention to this whole notion called a sigma field. So right, for those who are familiar with those, it's quite trivial to think about. When you have information comes in, you can form an information filtration, essentially the sequence of sigma field, and each one is increasingly contains more information. The really simple one to remember or to illustrate is simply say, I have a bunch of variables. They are in particular order. I'm going to talk about the ordering is important here. That x0 is a constant term. So basically the sigma field generated by these, say, R, attributes or predictors or features, whatever you want to call them. And as R goes down, that you have a filtration gets richer and richer, right? So R here is what I would be calling the formally. The R is an index resolution. So the whole multiple resolution, in my way of thinking about, is you start with a set of filtration, start with information filtration, a sequence of sigma field, and how you define it, that's well determined by the problem. So basically, now I'm going to go on with that notion and to see how far we can push. So at each resolution level, I'm going to define what do I mean by signal, what do I mean by noise. That turned out to be incredibly simple and incredibly intuitive. At least this is the one common way. I'm sure there are many, many other ways to define it. I'm using L2 norm here for a particular reason, but also for the common, everybody use, most people use L2. There are L1s as well, of course. And the at least for the L2 norm, that the signals are simply the conditional mean, or conditional whatever that group or stratification or sigma field you're in, and the noise is simply the variance at that level. Okay, so at every resolution, I can define what's a signal, what's the noise. So you immediately can see that by doing that, I can do the usual normal decomposition, right? Or called the Pythagoras theorem, and you're basically saying that the resolution, the noise at the resolution R itself can decompose into a resolution at the higher level, the noise at a higher level, as well as the difference between these means, the group means that I was not able to capture at the lower resolution level, right? So this is the simple ANOVA decomposition, and that holds for any R and any RS. So the difference in these conditional mean, by going from, by not being able to do at the S high level, only doing lower level, that difference itself, now, once you ignore the difference at the lower level, that become part of the part of the variation. That's exactly is what the waveless decomposition tells you. If you move some high resolution, low resolution to high resolution, then they start to become noise, right? Now, here's the interesting exercise that I did initially purely just for the fun, but then it actually leads to something incredibly interesting. At least I hope I convince you. It's really, really interesting. You can do this in a telescope fashion, right? You can keep going, right? You can have, so I did with R, start from R, then S equal to R plus 1, R plus 2. So you can write down this whole thing. Then once you write down this whole thing, you realize quite a few things here. First, you will see that essentially, at least in this framework, there's no such thing actually really called a variance. The variance is essentially all the biases that you did not include. They accumulated. So at the low resolution, they looks like a variance to you, but at the high resolution, they become, because as you have more and more to explain those things, then they obviously becomes signal, right? So you can see that I can do this telescope. This is like what I call the total resolution bias, because these are the resolution I did not model if I stop at the level R. But there is something quite interesting that you do stop at, there's an infinite level. After you do this, you realize there is something called a sigma infinity. Now, that is, you cannot just assume it's a zero, because this decomposition did not tell you it's a zero. You can certainly do a limit. You will find there will be a sigma infinity sits there, right? And when I look at this expression, I suddenly realized, I said, aha, I finally understood why there's this debate about whether the world is stochastic or it's deterministic. It all depends on how you treat this quantity. If I believe the world is deterministic, which means that if I could have collected data on every possible attributes for the individual, including environment, including everything, I would know exactly how the outcome of the treatment turned out. The only thing that becomes random is because we do not know that. So the uncertainty randomness is essentially a proxy for our ignorance. On the other hand, you could argue, somebody else say, wait a minute, I believe that the world is fundamentally stochastic, meaning that even if you could possibly exhaust all the collected information, hypothetically in real life, you can never do that, but just conceptually, you can collect everything. Somebody will say, God is still going to play a dice with you. The God is still going to be flip a coin in the end and say, hey, I got you. The outcome could be still random, right? So when I look at this thing, I say, this is interesting. Although I've told myself, well, this is more like just a kind of a philosophical musing. Since in real life, at least as far as we understand, I will never be able to collect data to really do hypothesis testing whether this thing should be zero or not zero. So that's my initial thought. I said, well, if that's the case, who cares, right? For my modeling purpose, for practical problems, I could either assume the zero or not zero. If it's not zero, I'm basically coded that into the total variation, just like anytime we do regression model. None of us really believe the regression model is exactly right. Whatever we cannot capture, we push them into the variance term. So initially, I convinced myself that I work with Shenren. I said, let's don't worry about it. Let's just assume it's not zero, right? But during the study, we realized, and Shenren reminded me, then I realized, holy cow, there's something quite different, whether you assume this guy is zero or not. And I want to share with you in the next few slides. And I think this does have an implication to this phenomena. Currently, we all kind of get puzzled why you have this seemingly incredibly saturated model in deep learning, other fields where seems like people don't suffer this overfitting problem, right? So I'm hoping that what I'm presenting here is a possibility. It's just a possibility. There's an alternative way of thinking this whole thing that that may give us some insight why that can happen. Okay, so now let me put down some general investigation. Then I will go to a specific example, and that would be really illustrate what I was just talking about. From what I just done here, that you can see that you essentially think about why me is your outcome from this treatment, and whatever the U hat R2D is your estimated. So you can decompose the errors in this in this additive fashion into three terms, right? If you choose any particular resolution, that's like choosing a model. You will suffer the what I call total resolution bias, which essentially is a model selection bias because your model only using R attribute. But even you choose this R attribute, you still need to estimate them, right? So that's what familiar estimation errors. But don't forget that in this formulation, when you think about go to infinite resolution, even you have everything, there's still, right, as I said, the work can still be stochastic. So you will have an intrinsic variance. So this one decomposition essentially captures everything we do in terms of, model selection, bias, estimation errors, and as well as these intrinsic errors. So I'll be careful here that I use hat for estimation, use 2D for selection. And the whole question is how big should R be, R2D be? Well, that's essentially the holy grail of statistics, inference, and prediction, right? Where do we stop when we choose a model, right? So this essentially is the equivalent to the Bias-Variance trade-off, as I already said, but the resolution framework does lead to some surprises, and I hope that you would agree with me. I also want to acknowledge that the mathematical setup here is almost identical to this kind of a sieve method for non-parametric estimation. For those of you who are familiar with that, you essentially, because the parameter here is infinity, infinite dimension, you're basically trying to let the dimension of your the approximate estimate go up in certain rate, so you can get those things. So this is a very similar in the sense that I'm choosing the resolution level, which is essentially a model selection, and which of course once I choosing a resolution level, then my number of parameters will be finite, and so that let that go. Okay, so that's essentially is the setup. So now let me talk about this example, and which is where the surprise comes in the first place. So I'm going to set up just like everybody else. Start with a linear model. The only thing different is I'm going to set this linear model with possibly infinite dimensional attributes that it predicts. On top of that, I can still put on an epsilon, which is like the intrinsic errors. The tau square here is the variance essentially of the intrinsic error at the infinite resolution. Again, for simplicity, I'm going to assuming everything is jolly normal. Obviously, you know that you cannot have all the betas arbitrary. The beta have to satisfy these L2 norms of themselves. You have to be finite, otherwise the thing will explode. But everything can be done, very nicely. Okay, so now what I'm going to do is say, okay, I'm going to choosing a particular resolution. What I want to do here is now, suppose I have data, and this is a model. I want to say, of course, I cannot use infinite many attributes. I don't have this infinite many attributes in real life. I want to say the theoretical study, what will be the optimal R, right? Where do I stop? First, you want to say, okay, how would you do the estimation? Since it's a linear model, I'm just going to do the ordinary least square. The ordinary square estimate itself will have a familiar, variance for the estimator. It will involving the intrinsic error. Okay, keep in mind the tau square here it could be 0. That's the whole thing, but it may not be 0. But either way, there's intrinsic errors here. Now there's something may look slightly complicated, but it's simply the residual error. Suppose I stop at the resolution R. Then anything I have not captured, all the other conditional variance as the resolution go higher, they become all the residual errors. If they add them up, that's essentially is what, it's like the R square decomposition in the regression, right? Whatever terms can be explained by model, whatever's left, we call the residual errors. Okay, so now here is the formula that I want you to, we're going to spend a little bit of time on this because this one is incredibly important to understand. There is an interesting phenomenon that we have not paid too much attention to it before. The idea here is that, okay, now I'm going to look at the estimation errors, right? I mean, this is the L2 norm of my errors. Now, this error when assuming the normal, particularly I'm taking the expectation, with respect to the training population, because again, this is all about collecting data from a training population or approximate population to infer about you, and you now become a person. Statistically speaking, called exchangeable with the population, right? So if you look at this variance of the beta, you can write down exactly, and this is where my wonderful students, Shenren's contributor come in. His calculation obviously is not hard to do, but he can just do everything just once without ever going back. I'm the one basically doing the checking. Now, what's important is that if you look at this expression, you realize this looks very familiar. Well, yeah, there's a degree of freedom. We have R-2 because remember there's a beta 0 term. We also have a variance term. So you have and this is degree of freedom. Now look at the numerator. Can you see my cursor when I'm moving? Can you guys see where I'm indicating? Okay, great. There are two terms here, right? There are the intrinsic error, tau square, there's the residual errors, right? So now you see here's the key thing. If the tau is bigger than 0, and we know AR is going to go down to 0 as you fit more and more term, at least theoretically, if you have infinite amount of data, the AR is going to 0. But as long as tau squared is bigger than 0, the numerator will be always positive. Therefore, if the denominator, if the R getting close to n-2, the thing is going to blow up. That's where we typically tell people don't overfit. Don't have your model parameter close to close to your sample size, because you're going to have you will have this infinite variance. Things will go wrong. But that is only true if tau squared is bigger than 0. What if tau squared is equal to 0? What if the system goes to infinity, but there's no intrinsic errors after you really have all these attributes? In which case you have a phenomenon that the AR itself is go to 0, right? And so you now have a phenomenon. If R approaches n or n-2, you will have a phenomenon which is 0 over 0. Now, as everyone sitting in this room should know, 0 over 0 is not necessarily 0, right? It could be 0, it could be anything, it could be different, depends on how these rates go down. But it gives you the hint that if AR goes down fast enough, in the next slide, I'm going to show you, if this guy goes down exponentially fast, if the residual error goes down exponentially fast, you can see that this whole thing can be still 0 even when R approaches n, which means that you don't have the overfitting phenomenon. As long as the residual error goes down fast enough, right? You should use as many data points, as high resolution as you can. Of course, you don't want R equal to n-2, right? Then no matter this is going to blow up. But you can use it very close to it, and you don't have that. You don't. But that's only happens when tau square equals to 0. Okay. But this also gives us an insight of how you have this whole thing about the double descent phenomena, right? Because many of you know in the machine learning there's an interesting phenomena that it seems like the model is overfitting, but then then it seems goes down. But once you understand this thing, now you can see that if the tau is bigger than 0, you can see when R approaches, how this thing is going to go up. But then afterwards, you do rigid regression, do something else. When you plot against the gamma, which is p/n, p here in the literature is the number of parameters. For me is is the resolution. You can see how this thing go up and go down. But once I understand this phenomena in this filtration setup, right? I can now create not only just double descent. I can create any descent, any number of descent as I want, because all I have to do is let me just show you, right? All I have to do is I keep adding attributes that are important. Then I throw a bunch of attributes are not relevant. When it's not relevant, it doesn't help to improve the approximation errors, but it will increase the variability of these of these prediction errors, because you throw a bunch of covariates is not relevant. But then you start adding relevant covariates predictors, then things go down. So you can see once you have the mathematical formula, you can have as many descent as you want, right? So this is just another way. I know that double descent has been debated about, but I just reminded people that this phenomenon can happen in many ways, and here is certainly a ways that very easy to explain what's going on. And I'm not even in the overfitting regime. These are all in the the sample size is the number parameter is less than the sample size. Even in these regions, I can create these phenomena as much as I want. So I'm going to give you some general results about this this phenomena, but now let me also talk about. I just talk about that using the linear model, which is continuous parameter, infinite dimension. But now let's look at the non-parametric setting. This essentially is a regression tree with potentially infinite depths. And to make life easier, and in the paper we actually generalize this, but here just let's say you have all these attributes. They're RID Bernoulli's, half and a half. And your Y's is completely determined by this tree. It's like ask 20 questions. And so now we do not define how deep this tree is, so the tree can potentially go to infinity. So you are now going to predict the Y using whatever the cells that you can you will have data for. There is a complication with this kind of setup because soon you will run out of sample. So a particular cell determined by these tree branches may not have anybody in it. In which case, the one simple thing to do is you say, if I don't have sample size in it, I go back to find the next resolution for which I have enough sample, I take average and I use that for imputation. So essentially, I'm again say, if the resolution is too high, I go back to the lower resolution where I do have data. So this is what we call the highest resolution imputation. May or may not be the best thing to do, but it's certainly a reasonable thing to do. So with this setup, we can also do all these calculations. Again, just like what we did before, there's a approximation error, there's the intrinsic error. Now you have three terms instead of before, because now you have these terms caused by whether the cell has zero or not, which they're part due to the imputation. The important thing to remember, and the detail here is obviously too much is in the article. The important thing to remember here is always determined by essentially the intrinsic variance as well as the residual variance. So now I want to show you that where do all these leads us to in terms of the theoretical results. So basically what we did here is we use the resolution itself to do essentially the model selection, right? How high thing you want. But there's a residual error. Essentially is another way to model sparsity. So I'm going to assume now this residual error has different rate of decay. So every time I put down a specific rate of decay, that tells you that how sparse the problem is. Of course, the faster decay is just assuming there's a fixed number of parameters. That's a traditional parametric way. But let's do a little bit better than that, right? If I assuming this decay rate is exponential, that's a pretty fast sparsity, right? And it probably that probably still covers most of the most of the large p small n that kind of study. And but this rate itself is saying that if you have certain covariates are very important at the beginning, but their importance scale goes down quickly as exponential rate. I can put down as polynomial, I could put down as log. Okay, so what I'm seeing here is now for each this assumption of the decay rate, as well as assumption on estimation errors, whether you're doing parametric kind of a model or the non-parametric model. One is like if you're doing the regression alpha equal to 2, if I include all pairwise interaction, alpha equal to 3, if I want a 3 with intact, so on and so forth. And alpha to R here is again the resolution. Alpha is the number of categories. If you're doing the categorical data, then it becomes exponential. But the key thing to remember here, and I know I'm running out of time, I'll be stopping in just 1 or 2 minutes, is that at this combination, if you have decay rate, if the sparsity is exponential and your estimation is like a linear model, you can show the optimal R when tau squared is bigger than 0, okay? If you do have intrinsic variance at infinity, your optimal resolution should be on the log n rate, and the optimal prediction error you can achieve is pretty much like the parametric one, except that you pay a log n price. Okay, that's the thing. But once you go beyond that, once the decay rate becomes slower, these are like a non-parametric kind of rate, and then it becomes log, essentially saying you cannot learn much. So the here's pretty much is like the classical results. The surprising part is what happened when tau squared equal to 0. That's the next slide. When tau squared equal to 0, you will see that in this linear regression case, you can actually really fit the number of parameters. The optimal choice is actually n minus Cn. The Cn here, the only restriction here is Cn had to be less than equal to 3, I think. Yeah. So there's this is like a constant here. But in this case, you can achieve the rate. Your optimal predicted rate is exponential decay. It's not the usual parametric ones. In the case when tau squared equals to 0. Once you hit the regression tree, this is also a surprising part. The regression tree, the infinite regression tree, you still can pretty much recover the kind of parametric rate if the tau squared equals to 0. All right, but once the decay rate is lower than this exponential decay, then you're pretty much getting into this region essentially not possible to run because the rates are so slow. So I don't have time to talk about the ordering, so I'm going to skip that. If there's time, I can go back. But I want to show you just the one simulation, and I'll stop there. Here is I'm using the linear models, and this is the simulations that the black curve is the actual theoretical mean square error, for this prediction. The blue line is from the cross validation, and the red one is from Stein unbiased estimation, and the dot one is using some information criteria, which is really quite terrible. So we're basically saying that here's the resolution, right? So this is saying in practice of what you do, if you have cross validation, you can try to estimate where the R is. Let's see, there's R here. That's the smallest R. And this for this tall example, I think this was based on sample size 500. These are cross validation, unbiased estimation, all did a pretty reasonable job. Information criteria does not really work. This the top row I'm showing you is when tau squared is bigger than 0. These are the settings where you do have you still have intrinsic variance, meaning the world you believe is stochastic. In those cases, you can see that these are classical kind of bias variance trade-off. If you fit too many things, it will start to go up. And these 3 different pictures from left is this is exponential decay, polynomial decay, normal log decay. The surprise comes here. Now, if the tau square equals to 0, then the picture started to change, especially for the first one. As the theory predicted, now you no longer have this kind of a bias variance trade-off thing. Essentially, you have no variance to speak of. You basically say, keep fitting it. Go as high as possible, all right? Until you really run out of sample size at all. You see the empirical rates also goes down. This is both theory in empirical rates goes down. Just saying, don't worry about overfitting. And now for the polynomial, for the logarithm, you do see the still goes back, but even there you can see the optimal solution gets pushed to the right a little bit, right? So basically saying you can try to fit a little bit more. Okay, so this is the kind of interesting phenomenon we did not expect. When you have sparsity strong enough, like exponential decay, that then you can avoid this overfitting if your system essentially is deterministic. Although manifested in the final population is always stochastic, because you also have all these other terms you do not have data for. Okay, so this is just let me stop here. For those who just wake up, for me, myself. So I want to just emphasize the big data for individualized inference predictions that the statistic for me, at least in this formulation, is really become an approximation scheme instead of inference, because it's always about approximating individuals from the proxy population. It's not about unbiased. It's not about induction. It's really about approximation. And the concept of bias is really more critical than pure variance, right? As I show you, only at the infinity level you were thinking about something. There may be something really God plays the dice with you. There's variance. Everything else in this infinite dimensional setup can be explained by something else. Okay. And so I've said in the stochastic world, we determine the the level of approximation bias variance trade-off. But in the deterministic world, right, as long as the decay is fast enough, which means the finite system you have really approximately is deterministic as well, then you don't really have the bias variance trade-off in one way. Or another way of thinking about it, you still have a bias variance trade-off, but variance is so small, or variance is essentially negligible, you put your whole egg in the basket of bias. So it's not a violation of bias variance trade-off. It's just the setup in which the variance become kind of a negligible negligible term, which I think is very relevant for this big data. People have been saying, oh, we don't need the statistics anymore because I have so much data, the variance is all kind of tiny. They're right in that sense. In the sense, you don't need the variance, but of course there's a whole bias we should study. And now what I'm showing you that all the bias itself is still in a form of variance. It's just a term that you have not modeled. All right. So just let me stop here. Just I think that the resolution to me is a really fundamental concept for scientific inference, because it is a low resolution renders all the operation meanings that we can do things. If everything is a completely high, infinite dimension, then essentially, there's not much you can do. I'm writing up this whole thing. The conceptual one is the part 2. Part 1 referred to my 2018 article about the integrating multiple sources. Sorry for running over for 7 minutes. My apologies. I should stop right here.
Thank you so much, Professor Meng, for your very stimulating and suggesting presentation. And now it's time to listen in the discussions. The first one.
Let me stop sharing.
Is Ruggero Bellio from the University of Udine. And then the second discussant will be Cristiano Marin from the University of Foscari of Wales. Please.
Okay, very nice to be here at this wonderful conference and to have the opportunity to discuss this very interesting paper by Professor Meng. First, I have some general comment. Well, as I said, the talk and the paper, the just paper that was mentioned in the paper is it's a very recommended reading. It's very thought-provoking. It really made me think about things never thought before. I believe there are 3 important topics that I want to attract your attention to. Well, the first one is transitional inference. We heard that is using data from approximating population to draw inferences on a new individual. Then multi-resolution theory. You have this information that increases without bounds. And well, what was very interesting is the method used to mathematically capture this concept, which is very delicate, by using the filtration that we saw a while ago. And then I believe it's very important is what happens in a deterministic world, because there are some surprising results. Like in a deterministic world, there are some may happen some counterintuitive things, like this phenomenon of multi-resolution effect that was mentioned. I think in machine learning has been some discussion about double descent in particular. Essentially, the idea is, the way I understood it, is you have a model with a lot of parameters that essentially interpolates your training set. Then we statisticians would expect that this is going to do terrible things in prediction. But instead, it does not. It has some resistance to overfitting in a sense. And so we hear today about the possible explanation of this thing. Here I'm just taking a formula from the paper, which is very similar to another formula we saw today. And this is a total average prediction error. And as we heard a while ago, you have this thing that in a deterministic world, the intrinsic error variance is 0. This resolution bias goes to 0 where R increases in any case. So this term is 0. But then you have here something that when both n and the number of predictors in linear models, they both increase to infinite, but the ratio converts to 1. This term goes to 0. So you end up having something that goes to infinite, that numerator, 0 here, and 0 there. So you don't know what really happened. And the term may not explode in a deterministic world. And so the optimal R may be close to the sample size. So you may have this interpolating model that does well. Okay, so this is a sentence copy and pasted from the paper. Implications of overfitting are not always obvious. There is a possibility for a black box procedure to resist it. I believe that's really important. I believe that another important point are some open points from the JASA paper. In the end of the paper, there is a mentioning of the role of regularization methods, because in large models, regularization methods are very natural, and so maybe this is something that will deserve some further attention. I don't know if whether Professor Meng and co-workers have been doing some further research about how to incorporate this theory about multi-resolution inference within regularization methods. And then in the paper, there is also the mentioning of the importance of systematic investigations of the deterministic multi-resolution framework for complex machine learning models. This is perhaps something of interest for machine learning, I would say. Okay, then as a further set of comments, I would like to do some personal notes, personal in the sense that are only vaguely connected with what we just heard, with the paper and the talk. The first one is about what happens in the setting of experimental methods for the analysis of the optimization algorithms. I've been collaborating with some computer scientists about these kind of things. Well, optimization algorithms here, I mean, like discrete mathematics algorithms for operational research kind of problems. Essentially, you have an algorithm which has a lot of tuning parameters, and for choosing them, you set up some experiments. But the point that some of these algorithms, they have some intrinsically random parts, such as simulating annealing. But there are also some algorithms which are purely deterministic, and we always give the same result for the same kind of choice for the tuning parameters. In short, this is an example, and this is a famous collection of articles of the deterministic world. So the message is that, well, deterministic world, they do exist. You can encounter them in research. Much more often than we statisticians will tend to think. Another thing that I was attracted by this trade-off between relevance and robustness. And this is very important and central in statistics. I think there is another example. Yesterday, there was a talk by Professor Candes about conformal prediction. And that's a very nice example, I believe, of this kind of trade-off. Because in conformal prediction that was introduced by Vogt and co-workers, and very popular in machine learning, again. But also then later was studied by statisticians. For example, a famous paper is by Ley and Wasserman. In conformal prediction, you try to get something which is predictions which are totally distribution free. So you go for very high level of robustness. But in doing this, you may lose some kind of relevance. For example, the basic version of conformal predictions, the one studied by Ley and Wasserman, where they only assume exchangeability, a little else. Well, in that case, you lose conditional validity. So you lose some kind of relevance. And this is the formula by Ley and Wasserman paper that quantifies this loss of relevance. So I think that was suitable since we had this talk yesterday about conformal prediction. Okay, in closing, I would like to attract attention on this COPS article that was mentioned also at the outset of Professor Meng talk. Well, COPS stands for Committee of Presidents of Statistical Societies. That's a very nice collection of articles, highly recommended. You will see some famous statisticians, including Professor Meng here. And there is this article, which is with this very attractive title, A Trio of Inference Problems That Could Win You a Nobel Prize in Statistics. Well, the first of these three problems is multi-resolution inference. And the part about the multi-resolution inference in this COPS article ends with three questions about this methodology. One is about covariate ordering. Second one is about trade-off between optimal sample size and optimal resolution R. And the third one is which is the appropriate resolution for testing. Well, I believe that the first 2 points are, at least to some extent, already addressed in the JASA paper and also today's talk. Although we didn't hear much about covariate ordering, this is well explained in the paper. I wonder if Professor Meng has some further treatment on this, and for example, if there are some new developments for the third item, which seems very important. Actually, the JASA paper mentions this forthcoming article with title Statistical Paradoxes and Paradoxes in Big Data, Multi-Resolution Inference, and Paradox in Individualized Treatment. Perhaps this title was changed from what we learned in closing, in the final part of the talk. But I wonder whether we are going to see this paper soon. And in that case, I'm looking forward to reading it. Thank you again, Professor Meng.
Thank you very much. The title has not been changed. I'm still working on the same paper.
Professor Meng's paper, I would like to focus mostly on digital medicine practice. Okay. Second discussant of Professor Meng's paper, I would like to focus more on the precision medicine practice. I really think that the Li and Meng JASA paper and the theory of infinite p-Zero-n is conceptually very attractive, and I really appreciate the elegant theoretical results that are written in the JASA paper. So in the last 2 weeks, I spent a bit of time reading something about precision medicine, but because I need to admit that was really, I mean, my understanding of topics was really very limited, and I learned a lot of things, so that was very nice. And my impression is that in order to move to the practice of application to precision medicine, there are additional sources of variation that have not been yet considered, but they are very important. And what I have in mind are problems related to measurement errors in the predictors, heterogeneity in the training population, and also the so-called occasion-to-occasion variability. These are standard problems that are commonly met in biostatistics, in econometrics, in application to social sciences, and many other fields. And statisticians, econometricians have developed a lot of methodology for this kind of problems. And but the problem is that handling this complication is often already difficult in much more standard setting than the Infinite-p-Zero-n framework considered today. So I start from measurement errors. My understanding is that as the number of predictors grow, we might expect some deterioration of their quality. So what I think is that the impact of measurement errors could be important, especially in those variables that are less relevant, but still important to refine the model and to make it more personalized. So are the variables that enter at higher resolutions. And so I'm wondering what is the effect of the rate at which measurement errors accumulate in this story. Also because there are additional difficulties that arise from the presence of correlation between possible mismeasured predictors. In Li and Meng Zaza paper, there are 2 simulation studies where predictors are assumed to be independent. And I don't complain about this because the paper is already very difficult and it would be extremely hard also to consider correlation. But correlation is present in the typical application, that the typical data that you look for precision medicine. And so my impression is that the ordering of the predictors in the filtration should not avoid to consider measurement errors and correlations. The second point is about heterogeneity in the training population, because the paradigm in precision medicine is that each of us is unique. But the problem is that also every unit in the training population is unique as well. And this means that, that if we assume homogeneity in the training population, we might dilute important efforts for the target subject. Okay, if we have all the relevant predictors and all these predictors are measured and observed with good quality, we can take control of the heterogeneity. But it's more realistic to assume that there is some missing heterogeneity that we need to handle somehow. And indeed, in many papers about precision medicine, there is use of random methods with a common and well-known computational complications that arise when we go out from the comfort zone of linear models with normal errors and uncorrelated random methods. The third point is that about occasion-to-occasion variability. We know well that the physiological fluctuations are important in medicine and they are important also in precision medicine. There is a very nice commentary about statistical pitfalls of personalized medicine written by Stephen Sin a few years ago in Nature, where it's written that the response is not a permanent characteristic of a person receiving the treatment. Rather, it varies from occasion to occasion. And this paper strongly suggests that what we really need is more N-of-1 trials, that are trials where one or more treatments are repeatedly tested on the same person. But of course, there are many situations where we cannot implement these trials or we cannot test all the treatments that we would like. So we need a training population, but we need to take into account the heterogeneity in the training population. And also we need some repeated observation to account for this occasion-to-occasion variability. So in synthesis, measurement errors, random methods modeling, longitudinal data analysis are classical topics in biostatistics that are important also in precision medicine. The problem is that the setup of precision medicine, the high dimensional setup, the very specific target, one single subject, make this classical topic from biostatistics hard to apply because they have been developed for much simpler frameworks. And that's all.
Thank you very much.
Thank you, Ruggero and Cristiano, for your discussion. And now I think Professor Meng has time to reply to the discussant.
I'd be very happy to, but tell me how many minutes or seconds do I have? Otherwise, I could have run another 2 hours.
You can start then.
Stop me, okay? Stop me anytime.
10 minutes, 10 minutes.
Okay. All right. Well, first, I want to thank both discussants that I think you summarized so well and you raised all these questions that I'm very glad that you raised, because part of the reason we work on this thing is trying to, raise this, all these issues that they're sometimes kind of sweep, under the rug. I really have many responses here, and I think most of which I will be, writing in this part 2, which I've promised for years, and I am working on it. And I would also appreciate it if you can send me your slides so I can make sure that I can answer these questions in this article that that I hope I will finish within this year. But let me just make a few general comments here. A general issue about first is regarding the deterministic versus stochastic. As a statisticians, we're so used to think about everything is stochastic, or at least the way we model it. And I guess in some sense, that's really the right way of thinking about it. There's one phenomena that I have been the editor for Data Science Review, Harvard Data Science Review, that I encountered is this notion of being randomness. The randomness is not that easy to communicate with people from other fields, from computer science engineers, from many other fields, because they don't think that way. Now, of course, we can say they should change their way of thinking, just think always. But I have to say that after I work on this thing, I realized that there are aspects of their thinking might be very helpful for us. So let me just this is part of the kind of thinking I have when doing this work. The whole notion of overfitting, right, bias-variance trade-off, is because that anytime we have a particular observation, we know that observation may not be on the exactly, let's say single regression, right? We know that observation is not going to sit on the regression exactly, because it can deviate somewhere. And it is a deviation we need to take it into account. If not, we will kind of tilting over, regression lines or the plate. But if the world is deterministic, in the deterministic world, that every single observation is a real constraint for the equation for the system you want to solve for, right? Because if there's no errors, then every observations will be, you want to use every single observation, right? So what the theorem we did, eventually, is the results, this exponential decaying is telling us when a finite sample, if there's a finite sample coming from this infinite deterministic world, when can you treat that approximately is like a deterministic system? So the idea here is that if something is decayed fast enough, then whatever the things that cannot be captured, that there can be, it's negligible that you can still treat the system as deterministic. If you treat the system as deterministic, you obviously want to solve it, put every observation there, solving it as much as possible. Now, what's the relevance of have that realization? This is very much the first discussant mentioned this. What I've been increasingly thinking about this phenomena of this black box phenomena. Well, think about the following: that these days these black boxes literally can have millions, if sometimes billions, parameters, right? They have enormous capacity to memorize things. This is the known term. The black box just memorize all the patterns. If the black box memorize all these patterns, if in the real world, all the patterns that can be observed are pretty much these are patterns that can be already observed by the black box in the training sample, at least probabilistically speaking, then the black box can do a perfect job or nearly perfect job. right? Because it does not need to understand any rules, because all whatever is remembered is the rule. So the question is, I think, for us to formulate, what I'm start wondering is a lot of these area where things seems like not overfitting. Maybe that's because the problem they're working on is approximately at that level become deterministic, right? The reason I'm saying this is, for example, we know these machine learning algorithms do very well in pattern recognition, recognizing, here the cats or dogs, all those things. But if you think about, there are just not too many types of cats and dogs out there, right? Compared to the complexity of the models they have set up. I bet these models will fail miserably if I ask them to predict how many hairs these cats and dogs have, right? Because then the resolution level will be much, much higher. So I think the way I'm thinking about it is that there may be, there is this kind of area where it's on the boundary between deterministic and the stochastic, meaning that there are lots of phenomena in practice, because the decision space in practice is what I call lower resolution space. Now, we talk about these clinical trial, these individualized treatment. At the end of the day, you have to realize the doctor do not have too many choices here. They either treat or not treat, or treat with a few different options. So the resolution level there is quite low, in the sense that you may do very high resolution diagnosis of all the decisions, but in the end, your decision space is a pretty low resolution space, which will actually, I think, help for lots of these kind of predictive algorithm AIs may work well, because they don't need the high resolution. They're not predicting things with very high resolution outcomes. So that's, I could be entirely wrong, but that's kind of the way I'm thinking about. And I would certainly encourage many of you to at least think about along the line, think about whether the system out there is, we now have the computing powers to approximate these systems practically. I'm not saying philosophically, I would not buy the notion the world is deterministic, but practically you will think about how many different patterns can exist there, that when I have enough, just like how humans, right? Like how children learn, that when I learn enough patterns, I don't necessarily understand why an adult is doing something, but I learn enough. Like training dogs, training animals, right? That's what they learn. They learn the pattern, and as long as the actual resolution space is with low resolution, I think that can be done. Regarding the question about all these variability, measurement errors, heterogeneity, occasion, absolutely fantastic questions, and you are absolutely correct that our paper does not treat that, and you are absolutely correct. The paper is already very complicated, and we certainly do not intend to be able to do any of those things. The whole idea of proposing this framework is at least hope that others will jump in, that we can all work together. But I want to also offer a different perspective here, that increasingly I'm trying to convince myself that instead of thinking about randomness, I'm increasingly thinking about similarities. I think that's a language that it's easier to convey to many other fields, but it also can be well modeled by probability distributions. We tend to use probability distribution to describe random phenomena or even uncertainties. We have emphasized less about distribution is actually a wonderful tool to describe similarities. In fact, description prescribes what similarity means. Let's say if I say you and I belong to the same distribution, I have defined a similarity. I define a similarity also allows we are being different, because you and I are just two realizations of the same distribution. We have a global kind of stochastic behaviors we share, but they're individually we can be different. And I think the reason I mentioned this, I think all of the issues about heterogeneity, occasion, variability, all those things, maybe that what's relevant here is these variations make them less similar or more similar to the individuals we want to study. So the question that if we can focus on using similarity as a common language, we might be able to incorporate all these different kinds of variations. I mean, there are many of them. I completely agree. As a statistician, I understand well all these decomposition, all these levels. But once you start thinking about the filtration framework, you realize that what matters is all these subgroups, right? It's all like whether I capture these conditional means or not, whether they are different or not. So I think that it might be a little bit easier language, at least conceptually, to think there's a way to proceed. Because otherwise, here's the problem. As the second discussant already mentioned, I completely agree again. Even in the standard treatment, the things already get so complicated. Like it seems like we're going to throw hands. And but first I want to mention that it's not like the framework I propose here makes things more complicated. The world is complicated. If you think about all these trying to approximate someone by a proxy population is a fundamentally complicated problem because it all depends on how you define a similarity, how you match it. So all these variations we're talking about, all the things I consider, we not consider, essentially they basically it drives a different kind of similarity. So what I'm hoping is that having a language where focusing on how do we measure similarity. So it's you know, I find myself probably start thinking more like a machine learners, right? You know, what they do is they put everything in the training sample, right? You say, you know, I'm going to change the training sample because everything is coming from there. For us, I think that this may not be a really bad way of thinking about, except that we go into those kind of thinking with the understanding where its problem is and where what are the principal thinking, what other things are probably just wishful thinking, and so that's I think that kind of a general comment that I have. As I already mentioned, the Harvard Data Science Review just published an issue on N-of-1 trial. N-of-1 trial is a fascinating area, and in fact, I think N-of-1 trial essentially is pushing what I'm trying to push in as well. How do we really think about very carefully? I was just talking to the editor of the N-of-1 trial yesterday. We did a podcast. She basically said, you know, in clinical setting, I mean, she's a clinical psychiatrist. He said, in the clinical setting, talk about real practice, right? I don't care about any of this study tells me how this treatment is going to work for this average person. I care about how I treat that individual, right? So I care about how do you find other people's looks like that that individual. There's not much randomness they're thinking about, but the concept of similarity works very well there. But I want to point out, though, also that we don't run into another illusion here. N-of-1 trial itself is full of challenges. And in fact, N-of-1 is not really N-of-1 at all, right? If you think about, and each of us, again, think about this highest resolutions, the moment, like every moment that we're evolving, right? When it goes through this period of doing a random trial on the same individuals, even we think there's a very strong requirement in this N-of-1 trial. They did it right, but I think itself should make us think. They need to say this disease or this treatment can be forgotten. Because if a treatment it puts there cannot be forgotten, then it can affect the next treatment, right? And that is a huge assumption. You know, when we age, whatever the medication we take, whatever thing we do, we improve, disapprove. So doing N-of-1 trial is really much better than we just do this and in a very ad hoc way. But I just want to point out, at least theoretically, in promising way, N-of-1 trial is not a panacea. Itself is going to face all kinds of problems. It's a problem. It's just you define. So I think the N-of-1 trial the literature really got this right. Look very carefully. They don't write N as a small n. They write N as a capital N. It's a capital N of 1. But they are just studying a population of one person. That does not mean a population of one individual. A person at any time crossing is a different individual in the sense of I formulated. So I think it's just pushing us into a much higher resolution world. And again, I want to thank both discussants. There are really a lot of you did a fantastic job in summarizing what I was hoping to get, as well as to highlight all the challenges we have. And you are also right that I need to finish that article as soon as possible. And so thank you again all for this occasion. And I really regret I cannot be there. I'm sure otherwise I can hear a lot from the audience. And if you are interested in this, feel free to email me. I'm happy to follow up with you all discussing this new way of thinking about stochasticity. Thank you very much.
Thank you so much again, Professor Meng, and to our discussant.